Hi, today we're going to look at this research paper. An image is worth 16 by 16 words. Transformers for image recognition at scale. In CNNs, an image is seen as a grid of pixels. CNNs use filters that slide across the image looking at small local areas at a time. These filters detect features like edges or textures in early layers and more complex patterns in deeper layers. CNNs assume sparse local connectivity, meaning each point in the image is only connected with nearby points. The information from these local areas is gradually combined to classify the entire image. Vision transformers take a different approach, inspired by techniques used in NLP. The image is divided into fixed size patches, typically 16 by 16 pixels each. This is similar to how NLP breaks text into individual words or subwords. Each patch is converted into a vector that describes its content. We call this patch embedding. In NLP, this is like converting words into word embeddings. Another vector is created to encode the position of each patch in the image. These two vectors are combined for each patch. All these patch vectors are fed into a transformer. The transformer uses a mechanism called self-attention to process this information. For each patch, the model creates three vectors: a query, a key, and a value. The model then calculates how much each patch should attend to every other patch. This is done by comparing the query of one patch with the keys of all patches. The result is a set of attention weights which are used to create a weighted sum of a value vector. This process allows each patch to pay attention to other relevant patches, regardless of their position in the image. In NLP, this is how transformers understand relationship between words in a sentence, even if they're far apart. Unlike CNNs, which build up their understanding of the image gradually, VIT can look at relationship between any parts of the image right from the start. This is because the self-attention mechanism allows each patch to interact with every other patch. Finally, the transformer's output is used to classify the image. The original research paper includes a diagram that illustrates the vision transformer architecture. Let's break it down. The process starts with an input image. The image is divided into fixed size patches, 16 by 16 pixels. These patches are flattened and linearly embedded. The special vector called the Learnable Class Embeddings Token, or CLS token, is prepended to the sequence. This is a special vector added to represent the entire image. It's similar to adding an extra patch that learns to summarize the whole image. The CLS token interacts with all patch embeddings through the transformer layers. By the end of the processing, it contains a compact representation of the entire image. This final state of the CLS token is used for classification. Learnable position embeddings are added to the patch embeddings to retain spatial information. Related sequence is fed into the standard transformer encoder. The encoder consists of alternating layers of MSA, or multi-head attention, allows each patch to attend to other patches. The second layer is MLP, multi-layer perceptron, processes the attention output. Then the layer normalization is applied before each block. Residual connections, represented by the plus signs, are used after each block. MLP head. The output corresponding to the CLS token is fed into the MLP head for classification. So what does the model learn? You can visualize the attention here. You can visualize the positional embeddings here that are learned. You can see here that the embeddings come out pretty sensibly. This positional embedding seems to largely recognize where it is in the image, even though you never tell it simply. You let it learn, but it relates to other positional embeddings that are in the same row or column mostly, and they're all sensible. You can see the filters it learns. So this is analogous to visualizing what CNN learns. And you can see it's similar to ConvNet visualizations. You get the same filters like these. And it learns like CNNs, but it's not programmed to do that. As you increase the depth of the network, the mean attention distance increases, and from the middle of the network, you pretty much have global computation. A CNN would look a line, would look like a line. And all the branchings in the top left, that's the gain that transformers can make. They can attend to very far away things at lower layers, unlike CNNs. So, by treating image patches like words in a sentence and using self attention, visual transformers can capture complex relationship between different parts of an image. This approach represents a significant shift from the local, hierarchical processing of CNNs to a more global relationship focused approach inspired by language models.